All right. Good afternoon, everyone. Morning, afternoon, depending on where you're joining this webinar. Welcome to everyone. Welcome to this Globant's Flip Thinking webinar. It is an honor for me to introduce today Juan Maldacena, who is one of Argentina, if not one of the world's premier theoretical physicists. Before introducing Juan, so this webinar is going to be recorded and shared. So for those who aren't able to catch up, we'll be sending a link after the event. And so Juan Martin will take questions, but we invite you all to use the questions, the Q&A feature of the WebEx to enter your questions. I will be recording them, and after Juan finishes his talk, I will present the list of questions to him as time permits. Before his talk, I will give a brief overview of a couple of projects related to astronomy that we're carrying through currently at Globant. But before we start everything, let me give you a brief biography of Juan. He was born in 1968 in Buenos Aires. He got his graduate degree from the Instituto Balseiro, a very prestigious institution here in Argentina. Then he moved on to Princeton, where he earned his PhD in physics. Soon after, he became a professor in Harvard, and then he moved on to the Institute for Advanced Study in Princeton, where he's a full professor to this day. His work in various areas of theoretical physics, string theory, quantum gravity, quantum field theory. He's most famous for what came to be known as the Maldacena conjecture, which is an idea that really has thrilled physicists because it not only puts string theory, a very interesting advanced physical theory for explaining particles, the world of particles and quantum physics. He puts that conjecture puts string theory on a solid footing and also solves apparent inconsistencies between quantum physics and Einstein's theory of gravity, which is one of the greatest challenges in modern physics. This conjecture has been described as a sort of Rosetta Stone that allows physicists to translate between what seem to be two very dissimilar worlds, the world of a very small and the world of a very large. Juan is a member of the National Academy of Sciences of the United States, the American Academy of Arts and Sciences. He has a very large number of publications, over 130 or more. He's received many awards, such as the Packard and MacArthur Fellowship, the Dirac Medal of the International Center for Theoretical Physics, and various very prestigious prizes as Sackler, Pomeranchuk, and Fundamental Physics. So we really have one of the big players in the world of science of the current day. Well, now let me give you a brief overview of a few projects that we're leading here at Globant before I hand it over to Juan for his presentation on black holes in space. Well, I should have started with this one. Oops. Move forward. There you go. So a bit of just a very quick introduction to myself. I'm a physicist too, but nowhere near the caliber of Juan. So I got my PhD in the University of Buenos Aires. I did a bit of research on galaxy formation, but then I moved on to the industry, and now I'm a data scientist here at Globant, working on various projects, mainly in numerical analysis, statistical methods, and simulations. And I'm going to talk to you very briefly about visualizing the universe at Globant Labs. So why an IT company could be involved in astronomy? Well, astronomy is a very engaging subject, which is not only it's one of the oldest, if not the oldest, arguably the oldest science, but it's ever new. It's something that keeps engaging our fascination, our interest. It extends our horizons and helps us discover our place in the universe and how grand, how magnificent it is. Also, it's one of the sciences that engages directly with the public. Some other sciences may be more interesting and useful, but very few sciences engage directly with the public and capture the public imagination as astronomy, astrophysics, and cosmology do. It also has been, on a more pragmatic side, it's been a cornerstone of technological progress throughout history, and it's promoted development in many areas over time, not only in the modern world, but even in the past, the development of clocks, of timekeeping, and currently in many areas of such as optics and electronic, and things that we encounter on a daily basis are derived from astronomical technologies. For example, one that's not very widely known, the wireless LAN, wireless network technology, has been derived from from radio astronomy development. So here at Globant Labs, what we're interested in is in applying the newest visualization technologies and machine learning techniques to help researchers with the work, and also to provide the general public with educational tools. So mainly in the field of astronomy, we have two projects ongoing. One of them is the Space System Project, and the other one is the NOVA Astronomy Legacy. I'm going to briefly tell you about both of them. First, the Space System Project. The goal of the Space System Project is to provide an immersive space adventure, kind of a space adventure and planetarium, which, of course, a planetarium software is not a new idea, but what we're trying to develop here is to take advantage of the latest technology in immersive technology, such as Oculus Rift, and motion recognition, such as what's been developed for games, as well known for the consoles like the Microsoft Kinect. And the goal of all this is to educate, to create an educational tool that, through a combination of gameplay and science, educates people on Earth and the solar system, our sun, our galaxy, the Milky Way, and beyond, and give an idea of the huge distances in the universe. So we're this is currently under heavy development. And the project aims to allow users to build their own tour of the cosmos, using real astronomical data that will be used to place astronomical objects in a 3D world, which the users can navigate in, maintaining real scales for sizes, for distances, and trajectories. The big challenge here is to find a compromise between providing a fun experience and also providing a true experience of the enormous universe, where the distances are so huge that to travel them, it would take years, months, years, or millions of years, maybe. So it has to balance interactivity and gameplay with providing actual real science. So the concept is to provide, like I said, an immersive experience. So we're trying to develop an environment where the user is surrounded by this feel of being on a virtual spaceship, inspired by those who have seen the TV show Cosmos. That's kind of our inspiration here. And well, the user will be provided with the options to select exploring space, scan planets, land on planets. And so when the user reaches different points in space, for example, now we know that beyond our solar system, there's continuous discovery of many new extrasolar planets. So the idea is that to be able to navigate between them, scan points of interest, and that will trigger possibilities to download open multimedia content, land on the planets, explore them when feasible, and so on. The other project is the NOVA Astronomy Legacy project. This is a joint venture with the new Argentine Virtual Observatory, that's the NOVA, which is an initiative of the National Scientific and Technological Research Council of Argentina. the goal is to is to achieve greater efficiency and productivity in accessing data and management of data of observation in many different wavelengths and many different sources. And also, that information would be provided to the research community at large, but also to the general public. One of the projects, the one that we're involved in, is what we call the Astronomy Legacy Project. So information from stars and galaxies comes to us as electromagnetic radiation. We cannot go and touch the stars, not yet. So what we know from the heavens is comes to us as light. It's the light that we can collect with telescopes, radio telescopes, and other sensors. A visual representation of the amount of photons that we receive per unit frequency or unit wavelength is what's called a spectrogram. And that's one of the fundamental tools of observational tools that we have. Before the era of digital cameras, this information was stored in photographic plates. And currently there are up to terabytes of information that remains on these photographic plates, which is a media that's very difficult to use and access and take advantage of. And using them is a skill that is being lost over time as people move on to better, more useful technologies. NOVA has a project to recover this historical information and make it available for further use. So here's an image of a typical spectra. So the spectra is what you see on the middle. So the horizontal length is the wavelength. So as you go, the light, as you know, comes from different colors, but also electromagnetic. The electromagnetic spectrum goes beyond what we can see to radio and X-rays and ultraviolet. So we have the spectra of an astronomical object, could be a star or a galaxy, and on top and bottom, the lines that you see on top and bottom of it are comparison spectra from a lamp in the laboratory that we used to compare. So the idea is to digitize these plates with a special scanner, extract one of the spectrums, scan it, count the pixel intensity lengthwise, and get a 1D spectrum that can be stored digitally. And that spectra is what is made available, stored in the database and made available to the community. We have to scan both the object and the comparison so that we can identify the different sources of light. The sources are the wavelengths that we're observing. This is a very challenging project because here's on what we see now is one of the typical images that we have to work with. So it's not as nice, clean as the image that I've shown just a minute ago. The typical spectra there are several per plate, so we have to identify and isolate them. But they are rotated, twisted, so that this twist and rotation has to be corrected. We have to identify the comparison spectra to know which type of lamp was used to emit the comparison spectra that was used in the particular image. And there are thousands of images to process. So we need this to be as automated as possible. This requires the application of the latest advances in computer vision. Otherwise, this will be very, very heavy and demanding work. And the goal is to develop an app that allows the upload and automatic extraction of spectra. We're developing our own code using Python and the OpenCV, Open Computer Vision library. And this is something that's also very challenging, very interesting thing that I'm particularly involved with. And something, I think it's a very, very exciting project. Well, that's all I wanted to say about astronomy at Globant. So whoever's interested can contact me directly. And now let me hand it over to what everybody came here to hear. So Juan's talk on black holes and space. So
hello, welcome. Can you hear me? Can you hear me? I hope you can hear me.
At least I can.
I need permission to share my desktop. Okay, good. Okay, can everyone see the slides? Okay, so can everyone see the slides? Can you see the slides, Tomás?
Yes, I can see them, and apparently, yes, here in the queue,
okay, very good.
the chat,
Great.
people are saying that they can see them. Okay, I'm going to stop my
okay,
video.
so I'll be talking about black holes and the structure of space-time. So I will be telling you a story about black holes and how they've been challenging for our understanding. And so black holes were invented by Schwarzschild very soon after the invention of relativity. He found the solutions. And they were confusing, so confusing that Einstein himself thought that they didn't exist. But then it was understood by Chandrasekhar that they are a consequence of gravity and that very massive stars can collapse into black holes. And then in the 70s, Stephen Hawking realized that black holes are actually not black, so they emit some radiation, and sufficiently small black holes can even be white. And he further thought that these black holes implies that quantum mechanics is incompatible with gravity. That was a suggestion he had. However, with modern techniques of string theory, we understood that gravity is compatible with quantum mechanics, and we also understood a certain relationship between particle physics and gravity that is particularly useful for understanding black holes. So my talk will be about describing this quick summary, but in greater length. So first, before we talk about black holes and so on, I'll remind you of some simple concepts about special relativity. So special relativity says that two observers traveling with constant velocity observe the same laws of physics. This is a principle that was introduced by Galileo about 4 centuries ago. And so it says that if you are doing your experiments in the lab and the laboratory is moving, you wouldn't notice that you're moving unless you were looking outside. But there's no experiment within the lab that can tell you that you're moving. That's the principle. Now, there is a second principle here for special relativity that was introduced by Einstein, which is that there is a maximum velocity for signal propagation, which is the speed of light. So this will be a new law of physics, which says that there is a maximum velocity for signal propagation. And this principle appears to contradict the principle of relativity at first sight, because if you have two observers who are measuring the same light, you might think that the one that is moving is actually going to measure a different speed of light. However, what Einstein said was that actually both see the same speed of light, but time flows differently for the two observers. So time flows differently for the observer that is moving relative to the observer that is at rest. But in such a way that both see exactly the same speed of light. And they also see different, they also see lengths differently. That's why I drew this one a little contracted. So the observer that is at rest sees the other one a little contracted. So one way to illustrate this is the following. So imagine you have two babies, two twins, and one of them remains at rest and the other one goes on a very long trip at very high velocities and then returns. Then the one that returns had time flow. The one that was moving had time flow more slowly and will be younger when they meet again. So one of the lessons from this discussion is that space and time form a single entity, which is space-time. We call it space-time. And the way we measure time, or the way we perceive time, depends on exactly how we move. But the whole space-time is the same. It's just that what we call space and time depends on how we are moving. So that was about space-time itself. So this is somehow the arena where physics will happen. And now we will be talking a bit about gravity. So our intuition is that, Aristotle's intuition is that heavier objects fall faster. And this is indeed true when the objects fall in air. But the idea is that if you remove the air, then everything should fall in exactly the same way. That's again some principle that was found by Galileo. And this is something quite surprising, that everything falls in the same way. So independently of the constitution of the body, in a gravitational field, any particle follows the same trajectory when it's really moving. And this is a new law of physics, sometimes called the equivalence principle. So this says, for example, that if you are orbiting the Earth, the spaceship and the astronaut will be following exactly the same trajectory. The gravitational field of the Earth will make them move in exactly the same way, so that they feel they are floating with respect to each other. And the same would happen if you take a plane and follow this zero-G trajectory. Okay, so in about 100 years ago, Einstein joined these two things, so the idea of space-time and the idea of the equivalence principle, into a new theory that he called general relativity. And general relativity is a theory of gravity, which says that gravity is due to the geometry of space-time. So the basic idea of this theory is that the heavy object curves the space-time around it. And then when you have a particle moving in that space-time, the particle simply follows the trajectory of maximum time in that space-time. That's more or less equivalent to saying that it's following the shortest path in that space-time. And so the equivalence principle is naturally incorporated because all particles are viewing the same space-time geometry, and for that reason they're all following the shortest path or the trajectory of maximum time in that space-time. And for that reason they're all moving the same way. So that's roughly speaking what the theory of general relativity says. And among the things, so a massive body deforms space-time, and in particular, I would like to focus on the deformation on time itself. So what this says in particular is that time flows differently for two observers in a gravitational field. So imagine that you are a person living in the bottom floor of an apartment, and you have a friend that lives in the upper floor. Then the idea is that in the bottom floor, the clock will run more slowly than in the top floor. Okay? And this is something that is seen if you have two clocks, and then you have two clocks that are really sensitive, very, very sensitive, then you can see this difference. And the effect is very small. It's 1 part in 10 to the 15, but it's an effect that was measured. And so we have another version of the twins paradox now. So we have two twins, and we take one into a region of high gravitational field, and then let him be there for a while, and then we join them again. We compare their ages. We'll find that the one that was in the gravitational field will be younger. So I mentioned before that Schwarzschild found the space-time geometry outside a massive spherical body. So what he did was he took Einstein's equations. So these are very concrete set of equations, and he solved it. He solved the equations to find the space-time geometry outside a massive body. And one of the things this geometry tells us is how time flows at different locations. So here I made a sketch of the star, and then we have the geometry outside the star. And out of all the features of the geometry, we focus just purely on the feature of the geometry that tells us how time flows. So we have a clock that is very far away that runs at a certain speed. And we have, as we get closer to the surface of the star, the clock runs more slowly. This is the same as we said before, that clocks run more slowly when they are in the presence of a gravitational field. And this particular solution that Schwarzschild found tells us exactly how this happens. And as you take that star and you make it smaller and smaller, keeping the mass the same, we find that clocks start running more and more slowly, so the gravitational field becomes larger. And there is actually a minimum size of the star, which we call the black hole radius, such that if the star is smaller than that size, then the time would not flow. So at the surface of that star, which is of that particular size, the black hole radius, time would not flow at all. Time seems to be frozen, and that is a feature of this solution. Now that is a feature that was surprising at the time, and it was believed that it was due to some approximation, and that when we do things better, this would not happen. And that this feature that the clock completely stops, it was believed that must be inconsistent and must be strange. However, it was later realized, and this was realized well in the first a little bit in the 30s, and then really more in the 60s, that the geometry actually continues behind the horizon, and that even though time seems to stop as seen from the observer that lives far away, if you were someone who's going through this geometry and falling through the surface where time stops, which we call the horizon, you would just go through this surface and you would not feel anything special happening at this surface. You don't feel anything special when you cross the horizon. But then the geometry in the interior contains a region which is called the singularity, where the gravitational field becomes infinite, and if you fall there, you would be completely destroyed. However, if you cross the horizon, then you cannot avoid crashing into the singularity. So once you cross the horizon, you cannot escape outside, and you will die at the singularity. Now, just to present an analogy for how this can happen. So this funny feature that there is this horizon, which if you cross, then you cannot escape. Let's think about the following analogy. So we think of space-time as a river. So we have a river, and the speed of the water in the river, it increases as we approach a waterfall. Now in this river, we'll have some fish, and this fish will travel at some velocity, which we'll call the velocity of light, or we call it c. It's analogous to the velocity of light. And so we have this fish, and if you have a region in the river where the velocity of the water is less than the maximum velocity at which the fish can swim, which is this velocity of light, then the fish can swim upstream, so it can avoid falling into the waterfall. However, if the fish is at the position where the velocity of the water is equal to the maximum velocity at which it can swim, so the velocity of light, then the fish will be stuck there forever, and it will not move relative to the coast. On the other hand, if the fish crosses this horizon and goes into the region where the velocity of the water is bigger than the maximum velocity at which it can swim, then the fish will inevitably fall into the waterfall. But the fish doesn't feel anything special when it crosses the horizon. So it's swimming and does not feel anything special at this position. So that's analogous to what happens to a particle falling into a black hole. So in summary, so the black hole has this imaginary surface, which we call the horizon. Once you cross it, you cannot get out. It was also understood that a star, a very massive star, can collapse into a black hole. And finally, there are actually objects in the sky that seem to be black holes. So let me talk just a little bit about the real black holes, the objects in the sky that seem to be black holes. And these come in two types. One type are the black holes produced by the collapse of massive stars. They have a size of about 10 kilometers. And the other ones are very massive black holes at the center of galaxies that have masses of billions or billions of the masses of the sun. And those are much bigger. Now, how do we see black holes? In principle, we could see them by noticing that they bend the light rays coming from the stars behind them. That's one possible method, though I think no black hole has been seen this way. But in other cases, the black hole is surrounded by gas. And for example, there are some stars that, some binary stars where one of the stars has collapsed into a black hole. And then the second star sends some extra material to the black hole. This material becomes very hot, and when it falls into the black hole, it emits radiation, and the astronomers see the radiation coming from this hot gas. So that's one of the ways in which we see black holes whose masses are similar to the mass of a star. There are also black holes at the center of galaxies, and so here is a picture, much larger scale object. So here, in the center of the left-hand side, we see a galaxy, that's the white part, the visible galaxy, and then we see very jets of particles that emit radio waves, and which are extremely big, much bigger than the size of the galaxy. And the idea is that those, when these things were seen, it was conjecture that perhaps there's a black hole at the center, and when things fall into the black hole, they gain a lot of energy, and part of this energy goes out and produces these jets. And now with better telescopes, one can see a region very close to the center where there is dust that is falling, and gas that is falling into the black hole. And so the right-hand side is an image closer to where the black hole is. The black hole here in this image would be very tiny, very, very small. Notice that the scale is 400 light years, and we said the black holes were the size of the solar system. That's of the order of light minutes, so it would be very, very tiny. But they concentrate a lot of mass and have a very big gravitational force. And it's believed that many galaxies, including ours, have these black holes at the center. Now, a common question is whether black holes are dangerous. And they are dangerous only if you fall in. The gravitational force outside the black hole is exactly equal to the gravitational force or the gravitational field of a star with the same mass. So if we were to replace the sun by a black hole, the Earth would continue going around the black hole in the same way that it's going around the sun. Of course, we wouldn't get any light, but other than that, we will not immediately fall into the black hole. Of course, the nearest black hole is very far away. And if you worry about the dangers of gravity, it's really far more dangerous to fall from a ladder. But black holes are very good for theoretical studies. And so now I'm going to start focusing on some theoretical properties of black holes, which are interesting, and I'll try to explain why these properties are interesting. So the first one is the universality. So the final shape of a black hole is independent of how it's formed. So it's only characterized by its mass, its angular momentum or angular rotation velocity, and its charge. I mean, stars can be very different. There can be blue stars, there can be yellow stars, red stars, stars with different chemical composition, etc. However, if the stars collapse into a black hole, the black hole will only be characterized by its mass. So all details about the chemical composition of the star that made it and so on seem to be lost forever. At least apparently are lost. They seem to all collapse to the same type of black hole. There's another interesting feature of black holes, and this is a feature that we can deduce from the equations, which is the so-called area law. It says the following. So imagine that you collide two black holes. So when you collide two black holes, you can emit some gravitational waves because the black holes are moving and they emit gravitational radiation. And so the final mass or the final energy of the total black hole in general will be less than the masses of the initial black holes. However, it turns out that the area of the horizon always increases. So the area always has to be bigger than the initial areas, the sum of the areas of the two initial black holes. And this is this physicists like this law because it's interesting. It's a simple statement about a very complicated process. So the equations that govern this process are rather complicated, but nevertheless we get this simple law out of them. So far we've discussed black holes according to Einstein's theory of general relativity, which is what we call a classical theory. So a classical theory is one in which the state of the system is completely specified at all times by the position and velocities, and then we can evolve to calculate what happens at later times using ordinary equations, classical differential equations. When we include quantum mechanics, we find a new surprise. And the surprise is that black holes actually can be white. And this was found by Stephen Hawking. Please remember, was there a message? Did they try to send me a message? No. Okay, so we can have white black holes. The laws of quantum mechanics imply that black holes emit thermal radiation. And the temperature is such that it increases as the size of the black hole decreases. So here I've given examples for the temperatures of black holes of various masses. So if you have a black hole of the mass of the sun, its temperature is very, very tiny. It's 10 to the minus 7 of the degrees Kelvin. So this is a temperature which is so low that it cannot be experimentally measured. So for astrophysical black holes, this is a very small effect that cannot be measured and has not been measured yet. However, for a black hole of the mass of a continent, which is 10 to the 18 kilograms roughly, the temperature would be such that you would see it white. So if you took the whole mass of a continent and you put it into a black hole, you would see a very tiny dot of white light. Okay, so as the black hole becomes smaller, it becomes hotter. So a big black hole is black, a smaller black hole becomes redder, and as it gets very small, it becomes white. Now, why is it that black holes emit this radiation? So it's related to, I'll try to explain that. So it's related to relativistic quantum mechanics. So we have, in quantum mechanics, particles can be created and destroyed. And normally you can have particles with positive and negative energy in the vacuum. They are constantly being created and destroyed. But in the vacuum, in flat space, the energy of an isolated particle has to be positive. So there is no net particle creation. So you might have all these pairs, but you'll never find an isolated positive energy particle out of the vacuum. However, in the presence of a black hole, the notion of, so the same pairs get created, and they have one with positive energy as seen from the outside and one with negative energy as seen from the outside. However, what is a negative energy particle as seen from the outside might have positive energy as seen from the inside, so the notion of energy doesn't coincide. And for that reason, both particles can now in principle exist, and one of them, the one outside, can go too far away, and that's roughly the origin of Hawking radiation. Now, this, what I said here, is a cartoon picture, but you can derive the presence of this radiation using the precise equations of relativistic quantum mechanics. So we've seen that a black hole emits radiation and it loses mass, so it can have a finite lifetime. And the lifetime of various black holes is the following. So, for example, a black hole of the mass of the sun or the Earth will live much longer than the age of the universe. A black hole with a mass of an ordinary object, say 100 kilograms, would evaporate in less than a millisecond. So it would be worse than a nuclear bomb. And masses of black holes, if you had a black hole of a mass of a mountain produced at the beginning of the Big Bang, then it would be evaporating now. We don't know whether those black holes were produced or not, but if we wanted to see this effect, this could be one way of saying it. If we were lucky enough that these black holes were produced at the beginning of the universe. So there is no evidence that these were produced. There are also some speculative theories where very tiny, small black holes could be produced in particle accelerators, but such black holes also would decay very quickly and are very different from these astrophysical black holes. Now, there are some theoretical problems with this black hole temperature. And this arises because these thermal properties of black holes mix quantum mechanics and gravity, and it leads to some interesting puzzles. And the puzzles, let's say, are two. One is why are black holes hot? And the other one is the so-called information loss paradox. So I will now explain these two puzzles. So first, before I explain the puzzles, let me remind you of our understanding of temperature. So this was understood in the 19th century, and we understand temperature as due to the motion of the constituents of the system. So, for example, you have gas in a box, you have the molecules of the gas are moving, and they are moving more slowly in a cold gas than in a hot gas. In the hot gas, they are moving more quickly. So, in summary, so heat is due to the microscopic motion of the constituents of matter. Now, there is an associated concept, which is the concept of entropy, which is the number of possible configurations of these constituents. So how many different positions these molecules can be in. And the first law of thermodynamics gives us this notion of entropy if we know the energy and the temperature. And in the case of the black holes, the entropy turns out to be proportional to the area of the black hole. And entropy can also be viewed as disorder, and the second law of thermodynamics says that disorder should always increase, or the entropy should always increase. And indeed, the classical area laws that follows from Einstein's equations says that the entropy of says that the area increases, and so that agrees with the interpretation of area as entropy. So these are so it's quite surprising that this classical fact, the fact that the area increases, has anything to do with the second law of thermodynamics, which arises in a completely different way. So the question is, what are the constituents of a black hole? So we've seen that the temperature is related to the motion of these constituents, but what are these constituents? And basically, they have to do something with the constituents of spacetime itself, because the shape of the black hole and so on is independent of the matter that made it. So we saw that different stars with different chemical compositions give the same black hole. And black holes could arise even purely out of gravity waves. So you don't even have to make them out of matter. And so this entropy has to do with the constituents of spacetime itself, and so to the structure and nature of spacetime. So that finishes the conclusion of the question, or the general question of the temperature of black holes. But the fact that black holes have this temperature is also related to the information loss. So we can form black holes in many different ways, but black holes seem to evaporate always in the same way. So you can throw different things into a black hole, different amounts of information, and it always seems to emit this featureless thermal radiation that has apparently has no information of the matter that made it. So according to laws of quantum mechanics, what comes out should depend on what goes in. And the fact that you have thermal aspects or you have thermal radiation should arise only due to an approximation, where you ignore the precise details. So this implies that there should be tiny subtle differences on the outgoing radiation which carry the information of how the black hole was made. On the other hand, if information was lost, we would need to modify quantum mechanics, and this was Hawking's view in the 70s. Since then, he's changed his view. And we need a theory that puts together quantum mechanics and gravity, and one such theory is string theory. So string theory is a theory, it's basically a theory under construction. It was started in the 60s with various developments along the way. It's a theory of quantum gravity. So quantum gravity means that it talks about the quantum mechanics of space-time. So Einstein's theory is a classical theory, and in a quantum gravity theory, you make space-time quantum mechanical. And it's a theory that reduces to Einstein theory under ordinary circumstances, so at low energies and long distances, it reduces to Einstein theory. And as we understand it now, we can describe in a complete way certain universes with negative curvature. I call them here imaginary in the sense that they are not the universe where we live, but it's a possible universe with gravity and physics, and there are universes where we can have a very complete description. You can think of them as model universes. And so the way these descriptions work, sometimes this is called holography, is that we can describe the interior of space-time in terms of a theory that lives on the boundary. And the theory on the boundary is a theory without particles. So in the interior, we have a theory with gravity, and on the boundary, we have a theory without gravity, so a theory on a fixed space-time. And it's a theory of particles, so it's a theory of relativistic quantum particles. So it's a simpler theory than a theory of quantum gravity. So it relates, this is a relationship that relates the quantum mechanics of space-time to a theory where you have ordinary quantum mechanics. And roughly speaking, the picture is more or less the following, that a simple particle moving in the interior is the same as some slightly more complicated set of particles that are strongly interacting and are moving on the boundary. And the advantage of this description is that we know the precise laws that govern this motion of the particles on the boundary. So that's the advantage of this description. And so using this, we can attempt to, we can describe a black hole. And so we can consider a black hole in these spacetimes. And a black hole corresponds to a large number of particles on the boundary in an approximately thermal state, so moving all randomly, but moving according to the laws of physics on the boundary, but a huge number of particles. And the temperature and entropy of the black hole correspond to the temperature and entropy of the particles on the boundary theory. So in these situations, you can actually calculate the entropy of the black hole in terms of the entropy of these particles on the boundary. So the theorem of this boundary obeys the rules of quantum mechanics, and so does the black hole in the interior. So black holes in this description are consistent with quantum mechanics, and this type of description is what made Stephen Hawking change his mind about whether black holes lose information or not. And this is definitely a definite prediction of string theory. Of course, it's a very difficult prediction to test. Now, in the meantime, people have been using holography to learn about strongly interacting theories. So here we think about the boundary theory as particles in our own space-time, and the interior as some extra curved 5-dimensional universe. And in this way, you can model heavy ion collisions at colliders like the Large Hadron Collider. And so one way to view the collision is as creating a new phase of matter. Or you can view the same thing as creating a black hole in a weird 5-dimensional space-time. So in conclusions, black holes are fascinating objects where the geometry of space-time is deformed in a dramatic way. Black holes and quantum mechanics give rise to interesting theoretical challenges. And string theory can describe black holes in a consistent way, at least as seen from the outside. And in this description, space-time is an effective or approximate concept which arises from more elementary particles living on the boundary of space-time. So there are many interesting open questions. For example, how to give a more complete description of the interior of the black hole, and also how to do these holographic descriptions for universes that look more similar to ours. For example, expanding universes that have a Big Bang singularity in the beginning. Well, these are challenges for the future, and for the time being, just thank you.
Okay, so thank you very much. Thank you very much, Juan. This is well, at least for me, it's fascinating. I hope it's been fascinating for everybody else. I'm sure it was. I think so. We invited you because so black holes and black hole space and the extreme phenomena in the cosmos are always. I find that they are engaging and very interesting for many people, regardless of background, regardless of whether they're physicists or architects or artists. They inspire, and they make us think about how surprising and how wonderful our universe is. Okay, so we have collected during the talk. We've collected a number of questions.
Right.
So we have, I think we have 10 minutes that we can use for a few of those. So I think one that is interesting that comes up often in discussion with people that are not very physics savvy is they get confused with this idea of radiation escaping the black hole. Once I encountered, so one of the questions was why, or sorry, how can radiation escape the black hole? Well, you kind of explain that with when you were going over the phenomenon of Hawking radiation. But one interesting question that is a variant of this and that I got asked once is that, wait a minute, if gravity is supposed to have a particle that mediates the force of gravity called the graviton, and the black holes have gravity, how can the gravitons produced by the black hole escape the black hole itself? How does the black hole affect the gravity.
Right.
That's a question that at least I find often.
Well, indeed, gravitons can be emitted from the black hole, and certainly among the particles that black holes emit are gravitons. And for example, for very big black holes like the ones in nature, they would be emitting photons and gravitons, so the lightest particles. Indeed, they can emit gravitons. And the basic idea is that you have this pair of a positive energy particle and a negative energy particle, and the negative energy particle falls into the black hole, reduces the black hole mass, and the positive energy particle comes out. That's the cartoon picture.
But this is not the same as, for example, when jets are observed being emitted from gas accreted from that's actually because that's not gas emitted from the black hole, but accelerated in the vicinity of the black hole, right?
Right. That's a different thing. So that's matter that falls into the black hole, and you might naively think that, well, all the matter can just fall into the black hole, but some splashes out somehow, and that's the thing that splashes out is the jet. So a little fraction that comes out is the jet, and other parts just fall into the black hole.
So because you mentioned that, one of the other common cartoon pictures that people have of black holes is like the gigantic cosmic vacuum cleaners that go around the cosmos sucking matter. But you said actually if you're close to the black hole but beyond the horizon, in principle you're not affected by it. So it's actually one of the questions was one of the questions was how does a black hole far away affect the Earth? So well, technically,
it affects it in the same way as a star far away affects the Earth. So very little or nothing.
So it may just be, I mean, we could see the radiation of, for example, gas being accelerated in its vicinity, or we could receive some of the Hawking radiation if it comes our way. But it's not that like it's pulling us towards.
Right, it's certainly not pulling us towards it more than a star. I mean, all the matter in the universe is pulling us in their direction. But things that are far away are pulling us so little that they don't produce any discernible effect. Now, the Hawking radiation is a very tiny effect for black holes in our universe because this Hawking temperature is much smaller than the temperature of the cosmic microwave background, which is the temperature at which photons fill the universe. And so actual black holes in nature are absorbing more than they are emitting. So
that's right.
We don't expect to see.
So one of the first questions is, I think it's interesting because it's one of the other things that one hears. Like I said, black holes are so fascinating that they get that they permeate our culture in many levels in science fiction and stories and so on. And one of the questions was about are white holes naked singularities, which is something that come up in stories or. So I understand that white holes are like very, very highly theoretical objects. Can you comment a bit on them?
Yeah. So. A white hole would be the time reverse of a black hole. So, so it's something that if you stand outside, you look back and you see a singularity. Yeah, indeed, we don't think that white holes will form out of ordinary matter. So the white hole would have to be there from the very beginning. So indeed, they don't exist. But I should mention that the interior of a black hole is rather similar to a cosmology. So the interior of an ordinary black hole is similar to a crunching cosmology, so cosmology where the universe collapses. And the interior of a white hole is similar to an expanding cosmology, a cosmology that has a Big Bang singularity. So actually, if we look at our own cosmology, it is somewhat vaguely similar as the interior of a white hole. So even though we never see a white hole from the exterior, we actually live in something that looks a bit like the interior of a white hole.
So one other question related to the previous one, why does a particle in the boundary don't drop into the black hole? Well, because it has...
Oh, very good. Yeah, that's a good question. So the idea is that these two descriptions are equivalent, and we should not think of them at the same time. So either you think of gravity in the interior, right? And then there particles can fall into a black hole or be emitted from the black hole. Or alternatively, you can think of particles which are confined to the boundary. And the two give the same description. So a particle in the interior that is falling into a black hole corresponds to a set of particles on the boundary that that expand and become thermalized with the plasma of other particles that exist there. So an object going into the interior of the space-time corresponds to a set of particles that is expanding on the boundary. That's roughly the idea. But the particles on the boundary are just confined to the boundary.
So here's another question that's it's interesting because I also read about that in the news. It says a few weeks ago, so Hawking made a statement about information and entropy of a black hole. The question says, he said the information is not lost, but so messed up that it's impossible to get something useful out of it. And he's asking whether this is a conjecture or is something that he has proven.
Well, the idea that information, if it comes out, should come out in a way that is not useful, that was assumed by everyone who thought that the information was not lost. This gauge gravity duality says precisely how garbled information is by giving precise laws of how information comes out of this type of black holes. Now, in his recent talk and paper, he had some idea of how information would be preserved, but I have to confess I haven't understood his idea, and I don't know there is anything concrete behind it. So maybe we'll have to wait till a longer paper.
Okay. So here's another one that someone that's puzzled about the time flowing differently for people on different stories of a building. He wonders, is that theoretical or literal?
No, that's literal. That's experimentally verified. You need a very good clock, but with a suitably good clock, you can verify that.
Of course, that hasn't been verified in buildings, right? It's been verified with satellites in orbit, if I recall correctly.
No, it's been verified in buildings. So there was a famous experiment. What's really been verified is the redshift of a photon as it falls in the gravitational field of the Earth using the Moss power effect, and it was verified in actually a tower in the Jefferson Building in Harvard University. I think in the 60s.
I think the flow of time, so the time flowing differently between for two observers is something that is one of the puzzling things. And well, one of the questions here is related. It says, do you think big studio movies like Interstellar, Gravity, or The Martian help bring science to the public? Well, in particular for Interstellar, I think the plot is strongly based on the flow of time. So the astronauts, I don't want to spoil the movie for everyone, but they move closer to planets that are orbiting a black hole, and they experience the effects of time dilation between one of the astronauts that stays behind and the other ones that go down to the planet that is closer to the black hole. What did you think that was an accurate portrayal?
I think that was pretty good. That was very nice. It illustrated very nicely what time dilation means, and and this would indeed, well, this is similar to this twin thing that I was mentioning, except that was very nicely done. But yeah, that's and I do think that it brings this concepts to the general public in a way that they are more understandable. Now, whenever these movies are made, of course, practitioners like us, we tend to sometimes complain about the things we don't agree with. Or they also travel back in time, and that's hard to that I think is not consistent with the laws of physics.
I wasn't very happy with that bit.
Yeah, so that part, but we can give them some poetic license to make the plot more interesting. But the idea that the episode that you mentioned of the people going to the planet with a big redshift and then the person outside aging more than the ones that went in, that's perfectly correct. Of course, the amount of fuel something that is incorrect is that the amount of fuel the rocket would need to escape is it's enormous.
It's probably much more than they would have at that point in the mission, definitely.
Well, yes. It's,
and one thing to say about going to the end of Interstellar, when they actually spoiler alert for people who haven't seen it, when they're inside of the black hole, and apparently they say, okay, well, inside the black hole time stops, so we can play around with it.
Right.
So it's actually, can there be a black hole without a, so it's actually two related questions. One of them would be, why do we talk about sizes of black holes?
Right. Well,
why do we talk about sizes of black holes, and also that they are a singularity where everything collapses to a point?
Right. So the size is the size of the horizon. So we can calculate the area of the horizon, for example, and if we take the square root of that, then that gives us the size. And so that's one measure of the size. Another measure of the size is you can measure the time it takes for you to fall into the singularity. So if you cross the horizon, it will take you a time proportional to the size to fall into the singularity. But indeed, well, that's the notion of size that we normally use when we talk about size of the black hole. But of course, in the singularity inside, well, this notion of space, the metric notions cease to be valid, so we cannot talk about the size. But certainly in the movie, the people fall into the black hole and nothing happens to them; they survive. But we think that if you fall into an actual black hole, you will die of the singularity.
Yes, well, the tidal forces at the horizon will tear you to pieces anyway. Yeah. And could you confuse one? So let's do just two more quick questions, and we can wrap it up. One of them is that could you confuse a white black hole with another astronomical object, such as a star, a quasar, a white dwarf?
No, a white black hole would be very, very tiny. So the wavelength of light emitted from a black hole is equal to the size of the black hole. So the size of this black hole would have to be of the size of the wavelength of light, of ordinary light, right? So for the micrometers or nanometers, okay? And it would be emitting very little light, but it would be very massive. It would be the mass of a continent. So it's certainly not, cannot be mistaken by any other thing, any other known thing. But also would be very difficult to see. I mean, if it is far away, you definitely will not see it.
And we'll get the final one. So they're asking, what's the difference between matter and information in this context? I'm assuming the context of a black hole. So it says matter in, info out.
Right.
So it would be, my guess is that it's the information of the, so you lose the information of whatever fell into the black hole.
Mm-hmm. Right. So, well, I mean, you can, the difference between matter and information. So suppose you have a book with words written, right? That has some information. Now you, let's say, burn the book, right? You have some ashes, you have some matter, but you don't have the information anymore, or you could erase the information. So it's not the same. So the information is contained in the precise arrangement of the matter that comes in or that comes out.
Very well. Okay. Well, I think we can stop here.
Okay.
It's been a very interesting session. It's a fantastic topic, and also a lot of questions. We also had a lot of attendees. This really has been a very, very great session. So I think on behalf of Globant and all the attendees, thank you very much, Juan, for your kindness and for your very interesting presentation. And well, it's been an honor to have you here with us.
Sure, it's a pleasure, and best wishes for all of you.
Thanks very much.
Yeah.
Okay, thanks everyone for joining us, and well, till next webinar.